I'm Andy, and this is a re-record of the talk I did at ACCU 2018 entitled Scheme Lisp, Feel the Cool. It's about how Lisp, and in particular the Scheme version of Lisp, is the best programming language ever invented, and I don't know why anyone bothered inventing any other languages after that. Hopefully by the end of this video you'll know enough Scheme to be able to write your own programs in it, and also have a really good feeling for why it's better than everything else. So what we're going to do is go through three main sections. We're going to talk about how simple Scheme is, how incredibly breathtakingly simple Scheme is, about how weird Scheme is and how strange it is when you're writing programs in it. And finally, we're going to spend a bit of time talking about just how cool it is and what it is that makes it so cool, and so much better than all the other rubbish we have to put up with the rest of the time. So let's start with how simple Scheme is. Scheme was designed to be simple. It was actually designed to be taught. It was used at MIT for the sort of introductory course to computer science for years and years and years. It was designed for that purpose, so it's designed to be extremely simple. That course was also quite mathematical in its approach, so it's designed to be a bit mathematical as well. And it was based on the ideas and some of the notation and some of the terminology from a bit of maths called the lambda calculus that was designed by, or invented by, Alonzo Church. Scheme itself designed by Sussman and Steele in the 1970s, and no one's ever done better. So first of all, how do you try it out? Well, if you're on Linux, it's really very straightforward to try out. If you just install a package called Racket and then run the command mzscheme, you'll be able to run all the examples from this video. You'll also find there's several other versions of Scheme you could use. You could try Chicken Scheme. Look around for a few other things if that one doesn't suit you. More importantly, Scheme is extremely simple to use and to understand and to write code in, so long as you're not reading some incredibly complicated code written by someone else. So the reason why Scheme is so simple is because it essentially consists of one thing that you can do and one data structure that you can manipulate. And actually, fundamentally, those things are really the same thing, and they look like the same thing when you're dealing with them. And right at the end, we'll look at how, in principle, in some fundamental way, they are actually the same thing. So, the syntax of Scheme can not only fit on one slide, it can fit on one line on one slide, and this is it. So all of your Scheme programs are going to look like this: an open bracket, and then something which is the operator, and then some other things which are operands. So this is essentially a function and its arguments. So you do an open bracket, and then the function that you want to call, or the procedure as Scheme calls it, and then the arguments you want to pass, which are these operands. And you can different functions can take different numbers of arguments, and every statement of your Scheme code is going to look like that. The only complication is that the things there that you see separated by spaces might themselves be other bracketed expressions, so they can nest inside each other. And there might be more than one of these lists, obviously. So let's have a look at a couple of simple expressions just to get you into what it looks like to write code in Scheme. It can be quite confusing at first. When I'm showing you slides like this with code on it like this with a little arrow at the beginning, that means I'm typing it into the interactive interpreter. So when I told you earlier on to type mzscheme, you'll go straight into the interactive Scheme environment. So you'll be able to type in expressions and then just see their value straight away inside there. Obviously you can run programs with mzscheme as well, but for the purposes of what we're doing here, we're mostly going to be just typing in expressions like this. So that little arrow is not something you typed, that's something saying start typing, and then the rest of the stuff is stuff we typed, so open bracket and then a plus, 3, 4 and a close bracket. So this is exactly an example of what I was showing you on the last slide. So the operator is plus, and then the operands or the arguments are 3 and 4, So when you ask for 3 plus 4, you get back the answer 7. So that's how you do something in Scheme. Open bracket, the thing you want to do, and then the arguments you want to pass in, and it gives you back the answer. So here's another example. If I want to use the operator star with 3 and 4, that means multiply, as you might expect if you've programmed in other languages, and you'll get back the answer, which you might expect, 12. So that's how you do things. But as I said, you can also nest these expressions, not just have one of them. So this is one bracketed thing with another bracketed thing inside it. So again, it's a plus. So the thing we're doing is adding together two things, and the two things we're adding together are 5 and this other bracketed expression. And the other bracketed expression is star 2, 2, which means multiply 2 by 2. So when we multiply 2 by 2, we get back 4, and then we're adding all of that to 5. So the answer is 9. And if you can read and understand what's on the screen now, you basically can read scheme code, and that's all there is to it. Almost all there is to it. So there's a few other expressions that look the same and have slightly different meanings. So for example, this is how we store a value inside what in other languages you might call a variable, or what we might say in Scheme, this is how you give a name to a value. So here, the name we're giving is foo, and the value we're storing inside foo is 3. So when we say define foo3, it doesn't say anything, but then when we ask what is foo, we just say foo, so that means please give me the value that's in foo. The interpreter will give us back the thing we put in, which is 3. So that's how you give things names. Now that we've got this name foo with something in it, we can use that in other expressions. So here we're multiplying foo by 4, so as you would expect, that gives back the answer 12, because foo is 3. And then the last type of expression that you need to be able to understand to understand most of the examples that we are going to look at in this video is the way of defining a function. So again, it just looks like open bracket and then some stuff separated by spaces and then close bracket. It's subtly different from the example we saw on the previous slide. So on the previous slide, we just said define foo. Here we're saying define and then opening a bracket and putting something in brackets here. And that's critically important. The fact that there's a bracket there means that the meaning of this is really different. So this means instead of define a thing which stores a number or something like that inside it, like foo did, we're saying define a function. So we're saying define a function called square, which takes in one argument called x. So that's what the square space x part means. And then the rest of the line is the body of the function, or basically what we do when someone calls square. What do we actually do? So what we do is we multiply x by x, as you might expect for a function called square. So this is the whole definition of a function, not just the declaration or something like that. This is the whole lot. So it's a function called square, takes an argument x, and the answer you get back is what you get by multiplying x by x. Notice there's no return statement or anything like that. A function will just return whatever you give as its body. And if you give more than one line of code as the body, which you can do, the return value is just the last line of that function. And that makes sense. We'll see why that can work for all types of things you want to do as we go on. So when we call square and pass in the argument 4, then hopefully, as you'd expect, we get back the answer 16. So we've defined a function called square, and now we can call it. We can also use it as a sub-expression of some other expressions that we're working with, like this. So here we're saying square 2 and then square 3, and then add together the answers, and we get back 13, which if you do the maths should be right. Okay, so now you know how to define functions and give names to things. Something else you're going to want to be able to do is do things like ifs, make decisions about stuff. So here we're defining a function called abs. So define means we're defining a function or a symbol. In this case it's a function because there's a bracket before abs, so we know that this is a function definition. So inside that first bracket it says abs space x, so that just means define a function that takes an argument which we're calling x. And then you can start a new line. Doesn't make any difference to scheme. It doesn't notice new line characters. So here we're starting a new line, and we're using the scheme convention of lining up all the sub-elements of a bracketed expression, lining them up with each other. So all the operands of an expression are all at the same indentation level, and the first one is on the same line as the stuff to the left of it. That's just a convention, but it's reasonably convenient. Most of your scheme code becomes reasonably easy to read if you use this convention. The hardest bit about writing scheme code is that there's a whole load of closed brackets at the end, and you never know how many you want. But it's okay, because most editors will tell you when you've finished typing enough closed brackets. Some editors will actually even type them for you when you make your opening bracket, which is rather nice. Anyway, so we're defining a function called abs, and the body of that function is all one bracketed expression. So in this case, it's a bracketed expression that starts with if, and that bracket ends on the very last line. It's the second last closing bracket. The last closing bracket is for the define, the one that starts next to define. So it's one line of code, logically. It's 3 lines of code on the screen, and it's an if. So this is how we do flow control. We say the word if, and then there are 3 operands to that operator. The first one is the predicate, or the decision we're making. The next thing after that is what we do if the predicate comes out as true, and the second thing is what we do if it comes out as false. So the first thing has to be something that comes out as either true or false. In this case, it's the thing written next to if, which we're using to make the decision. So it's open bracket and then less than x space 0 close bracket. So that means x is less than 0, is how we would say it in English. So that obviously does come out true or false. Basically, the less than symbol here is an operand, or you can actually think of it as just a function. So less than is like a function that takes 2 arguments, and it returns true if the first one is less than the second one. The scheme does have the idea of true and false, which we'll see a bit later on, but in this case that value is going straight to the if, so we don't have to look at the true and false to make the decision. We let if do that. So we're basically saying if x is less than 0, then return the result of running the minus function with an operand x. And if x is not less than 0, well, then just return x. So that last line is just return x, and the line above, the minus space x all in a bracket, means negate x, or what you might expect, minus x. So the subtlety here is that if you do open bracket minus and then multiple arguments, it does a taking away sum. If you give it just one argument, it just negates that argument that you gave it. So that's how we're using it here. So we're basically saying if x is less than 0, return minus x, otherwise return x. So when we run this, if you pass in minus 3, you get out the answer 3, and if you pass in 3, you also get out the answer 3. So that's the abs function working as you'd expect, and that's how we defined it. So that's how if works. Notice that if looks exactly like some of the other stuff we've been doing. It almost looks like it's a function. Now, it's not actually a function. If it was a function, this wouldn't quite work, because when you call a function, we actually evaluate and work and run the code of all the arguments that are passed before we then run the function. But in the case of if, we wouldn't want to do that, because we only want to run the half that's come out as true. So in this example, that wouldn't matter. But in an if where we're actually printing something out or something like that, you definitely only want to do the then part or the else part, not both of them. So if is not a function, but notice that in terms of syntax, it looks exactly like you're calling a function. And also notice that if returns a value, and that's the value which is used as the return value of this whole function. So if definitely is an expression and looks like a function. Looks pretty similar to if you just were calling some function that you defined in the body of your function. So yeah, so that was flow control, how to define functions, how to define names and things like that. So the other absolutely key thing you're going to need to understand to be able to write Lisp scheme code and to be able to read scheme code is these things called lists, and they're also very simple. Here's how we make a list. We just say list and then pass some arguments. And the way the interactive interpreter responds when we ask it to make a list is it prints it out like this. So if you read that wrong, it looks like it's another one of these bracketed expressions that we might be running. So it might look like we're calling a function called 9 or something like that, but we're not doing that. We're calling an operator called list, passing in those 3 operands, and the way the evaluator prints that when it talks back to us about it, as it makes it look just like open bracket 935. We can do stuff with lists. So for example, we can call a function which is built into Scheme or provided with Scheme called sort. We can give it a list of 9, 3 and 5, and we give it a less than, so it knows how to compare the things in that list, and it will give us back that same list but sorted using the less than function. We can also ask for the length of a list, and it will give us back how many items are in that list. So that length function is also provided with Scheme. So now you know enough lists, enough about lists to be able to work with the data structures that you come across in Scheme. Lists are used everywhere. They're completely fundamental, and in fact, the name Lisp, Scheme being one of the types of Lisp, is derived from the word list. It stands for list processor, list processing. So that was how Scheme is simple. This is how Scheme is weird. So you will find when you're reading other people's Scheme code, if you've never written or read code in a functional style, it's going to look pretty strange for you. The first thing we'll cover in the stuff being strange is that actually lists are not the fundamental data type in Scheme. Actually pairs are the fundamental data type in Scheme, and lists are built out of pairs, and I'll show you how that works. You'll also find that we use recursion to do all of the interesting stuff when we're defining functions. We either use recursion ourselves or we call functions which are actually recursive. And if you're not used to writing everything using recursion, that takes some getting used to, but it's also pretty cool. You'll also find that almost everything we're doing involves passing functions into other functions and returning functions from functions, and that can get pretty hairy until you get used to it as well. And then one of the other weirdest things about Scheme is just how much code and data are really just the same thing. We'll see some examples of how that's pretty weird. So first of all, let's examine a little bit more this thing we called a list. So let's make a list with 1, 2 and 3 in it, and then let's put that list into a variable or a name x. So when we do that, now x has got that list in it, and now we're going to call this function or this operator car. We're going to pass in x as an argument, and we're going to get back 1. So maybe that gives us a bit of a clue as to what car means or what car does. Now there's another function, or another operator called coulder. So when we pass x into coulder, and yes, that is, as far as I understand it, how you pronounce it, what we get back is a list of 2 and 3. So car gave us back the first thing in the list, and coulder gave us back all the other things in the list. So bear that in mind, we'll get there. Now let's have a look at another function. This function is called const. And let's give it 2 things. In this case I'm giving it 2 strings, A and B. That's how you write a string in Scheme. Just put it in double quotes. So these could have been numbers. This is just me taking advantage of the chance to show you strings. So when we call const, the evaluator prints out that thing that we've made as the string A and then a dot and then the string B, all in brackets. So it looks a bit like what it wrote when it gave us back a list, except instead of just being A space B, it's put a dot in between them, and that's how it writes one of these things that we are now talking about, which are pairs. So what const does is makes a pair. So we asked it to make a pair of A and B, and the evaluator printed that out as a dot b. That's just the way it prints out pairs. So let's do some more stuff now. Let's stick together 5 and 6 into this thing called a pair, and then use that thing as the first half of another pair. So we've made a pair of 5 and 6, and then we're making a pair of that pair and 7. So let's see how the evaluator prints that out. So this is how it prints it out. So it's 5.6 all in brackets, and then after that a dot and a 7, and then all of that in brackets. So you can see that this is two pairs. One pair which is the left hand side of another pair. So it's a pair of 5 and 6, and that pair itself is paired with 7. So that's fine, that's what const does. Const makes pairs. So why am I talking about pairs? I thought I was talking about lists. Well, let's continue looking at what these car and coulda functions do. So first of all, let's const together 1 and 2 and put that into a name p. And now let's ask for the car of p. So when we ask for the car of p, we get back 1. When we ask for the coulda of p, maybe you can guess what we get back. Well, what we get back is 2. Not a list containing only one thing, which is 2, but 2. So last time we used coulda, it gave us back a list of the remaining things in the list, or everything except the first item. And last time we used car, it gave us the first thing in a list. So maybe this is giving you a bit of a clue as to what lists really are. What lists, the reason why car and coulda can be used on a list as well as on a pair, because really car and coulda just mean get me the first thing and get me the second thing in a pair. But lists really are pairs. So let's explore a few more things, and we'll eventually hopefully be able to see that more clearly. So first of all, let's ask Scheme to print the value of this special word, which by the way is not always defined in all versions of Scheme. They kind of went off the idea of allowing the word null to mean this, but I like old versions of Scheme where it's allowed. There we go. So when we ask for null, what the evaluator prints out is bracket bracket, by which it means an empty list. But more interestingly, when we const 2 with null, what the evaluator prints out is open bracket 2 close bracket. Now what that means is a list with only one thing in it, which is a 2. So now maybe we really are getting a clue as to what a list is. So what we asked for was a pair of 2 and null, and we know that null is an empty list. So kind of what we asked for was a pair of 2 and an empty list. And what the evaluator said was, yes, you can have that, here it is. And by the way I write that is a list containing just 2. So let's continue fiddling about with consts and see what the evaluator gives us. So now let's pair up 2 with null, and then let's pair up 1 with that thing. So we know that pairing 2 with null gives us, well, it gives us a pair of 2 and null, but the evaluator is telling us that that is a list with just 2 in it. So when we pair up 1 with that, 1 on the left hand side and this list of just 2 on the right hand side, the way the evaluator prints that is the same way it prints a list of 1 and 2. So here if we ask for a list of 1 and 2, the evaluator prints out the exact same thing again. That's because they are actually the same thing. So in Scheme, the definition of a list is a chain of pairs like this, and then the last pair is null. So let me show you a diagram which might possibly make that easier or harder to understand. So lists are actually a chain of pairs. So a list of 1, 2, 3 is actually the const of 1 with the const of 2 with the const of 3 with null. And that's really what a list is. It's a whole load of pairs. The last thing of which is a null. If the last thing is not a null, the evaluator won't recognize that this is a list, and it will print it out in the way we saw before with dots in between things, because it's just, as far as it's concerned, these are just pairs with random stuff in. But this special type of chain of pairs is something that Scheme recognizes and knows that this is a list, so it displays it in a different way. It still really is a chain of pairs, but Scheme just displays it in this special way. So now, hopefully, at this point, you can understand why we got that slightly surprising behavior of car and coulda that we saw before. Basically, car gave us the first thing in the list, and coulda gave us another list with everything in it except the first one was missing. Maybe that makes a bit of sense now, because car, if a list is just a pair of, if this list we're looking at on the screen here is just a pair of 1 and the rest of the list, when we do car, we ask for the first thing in the pair and it gives us back 1. When we do coulda, we're asking for the second thing in the pair, but the second thing in the pair is all those other pairs chained down, which is still a list that ends with null. So coulda would give us back a list of 2 and 3. So these functions have strange names. Const sticks things together. Basically it makes pairs. Car gives you the first thing in the pair, and coulda gives you the second thing in the pair. And when we're talking about lists, const sticks something onto the beginning of the list. If you do const something and then a list, it sticks something on to the front. Car gives you the head of the list, or the front of the list, the first thing in the list. And coulda gives you the tail, i.e. the rest of the list. If you're interested in why they're named car and coulda, it's because Scheme is a universal language designed to completely abstract away any of the ideas about the functioning of the machine, the registers, the CPU, any of that stuff, and just be a completely general, beautiful mathematical theory. So they named car and coulda after the parts of the address register in the IBM 704 machine, I think, or some old, very old IBM machine which they were designing this on, completely failing successfully to abstract themselves from the ideas of the machine into a pure mathematical world. But there we are, we're stuck with it. And now that you know what car and coulda means, it should be pretty clear to you what cadder's meaning is. Right? Well, maybe not. But actually one of the reasons why these names have stuck is that they're reasonably easy to pronounce. So we can pronounce it cadder, and you can reasonably easily hear what I'm saying. And what cadder means is you just break up those letters A and D in the middle and nest them in this way. So basically it means take the coulda, and then the coulda, and then the coulda, and then the car. So basically that means take the coulda means look at the second item onwards, and then take the coulda again, it means take the third item in the list onwards. And then a coulda again means take the fourth item in the list onwards. And then car means take the first thing in that remaining list, so that's the fourth item in the list. So cadder means give me the fourth thing in the list. And you actually get functions. Scheme doesn't obviously give you an infinite number of functions with names like this. Maybe not obviously, but anyway, it doesn't give you an infinite number of functions with names like this, but it gives you quite a lot. And it doesn't just give you cadder type ones that you can use to look further into a list. It also gives you cadder and things like that, because there are other structures you can build out of pairs other than lists, where you might want to go through a tree structure, picking the first thing in the pair in some points in that tree, and the second thing in the pair at other points. So you'll be mixing A's and D's, not just a whole list of D's and then an A at the end. Anyway, yeah. So there's a whole load of functions. They're pretty weirdly named. This section is about how Scheme is weird, so hopefully that's appropriately weird. Other things that are weird, as I mentioned before, almost everything you do in Scheme you're going to do using recursion. So here's an example of the kind of function you might find yourself writing. Obviously you won't really be writing a function called sum, because there's already a function called sum, but it's a reasonably simple example of the way you write functions in Scheme. So here we're defining a function called sum, which takes in an argument called v's. It's the convention quite often, if your function takes in a list like this one does, to name it something s, which is kind of like the plural of v. So these are this would be pronounced v's as opposed to like verses or vs or something like that. So it takes in an argument called v's, which is some things which we are calling v for some reason. That's a sidetrack. Anyway, so it's a function called sum, takes in an argument called v's, and the function is all one logical line, just like we looked at before. Again, it's an if, so the whole of the rest of the function, the whole of the return value of the function is just the result of this if expression. So the first thing you pass to if is a yes or no question or a predicate. In this case we're asking, is the length of v's equal to 1? So that's basically using the equals function with two arguments, 1 and the length of v's. Remember we saw the length of v's before. So if the length of v's is 1, well, what's the sum of a list of length 1? So by sum I just mean add up all the elements. There's only one element, so the answer is car v's. So that the line immediately below the if is car v's, and that just means take the first thing in the list, and the answer, when you're adding up a list and the length of that list is 1, the answer is the first thing in the list, which is which is what car v's means. So just give me the first thing in the list, and then the bottom two lines of this function are the rest of the definition of the function. So these are all the else case of that if. They're spread over two lines on the slide, but it's really one expression, which is a plus expression, which adds up two things. It adds up the first thing in the list to the result of calling sum on coulda of the v's, where coulda means the rest of the list. So basically add up the first thing in the list and the sum of the rest of the things in the list. So that kind of makes sense, but you'll notice, well, if we run that, you can see it does indeed work, but you'll notice when we're doing this that we're calling sum from inside itself. So if you're not familiar with recursive functions, this is pretty confusing. So how can you call a function from inside that same function? Well, actually it works perfectly fine. It even makes sense if you do it right. So in this case we are calling sum again, but we're calling it with a different list from the first list we were given. The first time we were called with an argument of v's, but then inside ourselves we call ourselves with an argument of coulda of v's, which means basically a smaller list, a list with one thing taken off it. So so long as you've got some things in your list, if you keep on doing this, you call yourself again and again and again, eventually you're going to call yourself with a list of length 1, and at that point you're not going to get into that plus expression at the end. You're going to get into the first part of the if, which just returns the first thing in the list. So once you've given back that first thing in the list, that's your answer so far, but now you've got all these other calls to sum that are waiting to get sorted out. So you return that value back and it goes into the plus, and it gets combined with the value that was waiting around to get plussed together with it, which was the previous thing, the second last thing in the list. They get added up, they get added up, they get added up, until eventually you come all the way out. You've added up everything in the list, and at that point the answer gets returned. You've added up all the things in the list. This can be really confusing, but so if you stare at it for long enough, you can see what that function's doing. The other feature of this recursion, when you're going through a list, which is often what you're doing when you're writing recursive functions, is that you're going to be calling car and coulda. Almost always the structure is going to be, if you've finished, then do something with the car of the list, and if you haven't finished yet, call yourself recursively with the coulda of the list. So that's what we're doing here. Just stare at that for long enough and you'll convince yourself that it's fine and it works. But actually, often in Scheme, we're not writing our own recursive functions, we're passing functions into as arguments to other functions, and possibly those functions do recursion. So this is something that I'm referring to here as meta functions. So basically functions that take in functions as their argument. So let's have a look at what we've got on the screen here. We're first of all defining a function called double, which takes in an argument called value, and the body of that double function is just this *2 value. So basically multiply value by 2, and that's the answer. So double does what you'd expect it to do. It returns double what you passed in. And then the more interesting function is in the middle there. So here we're defining a function called apply dash twice. And by the way, it's totally fine for you to have dashes in your function names or your argument names. In the middle of a word like that, Scheme is totally happy for you to do that. It knows exactly what which word is the function name here because it's everything up to the space. I told you it was simple. So the function, we're defining a function called apply twice. It takes in 2 arguments. One is called fun and one is called value. The fact that fun is called fun might be a hint to you that we're expecting that first argument to be a function itself. So this is a function which takes in a function as one of its arguments. And then the body of the function is that second line, which says fun, brackets, fun value. So basically that inner fun value means call function, or call fun, with the value that we're being given as an argument. Then get back that answer, and then use that answer as the argument to another call to fun. So this function is called apply twice because what it does is applies that function twice to the value that gets passed in. So if we've defined a function called double, we define a function called apply twice, and we pass in double as one of the arguments to apply twice, and the other argument we passed in is 2, so this is what's happening on that bottom line. What happens? Well, double gets called on 2, making 4, and then it gets called again, making 8. So apply twice calls the function twice. And you see that this kind of stuff all the time in Scheme, and if it looks weird to you, you should probably start getting used to it. So, yeah, we pass in fun, and then we call fun inside apply twice. Yeah, and as I was saying, yeah, you will write functions which take in functions as their arguments and also return functions as their return values, which is exciting too, and we'll get to some of the amazingly cool stuff you can do with that. But you'll also be using a lot of standard functions that take in functions as arguments. So map is a standard function. It takes 2 arguments. It takes a function and a list. And what it does is calls that function on every item in the list. So when we pass in double, it calls the function double on every item in the list. So here, each item 3, 4, and 5, it calls it for each of them, gets back the answer, and then it makes a list out of all those answers. So inside, map might be implemented recursively. We're not doing any recursion here, but we are passing our argument in, our function in, as an argument to map. So that was recursion and functions, metaprogramming, maybe passing functions as arguments. Something else that's weird is that in Scheme it's really, really easy to treat data as code or treat code as data. So let's define a name or a variable called s, and we'll put in it a list. And this is a list of 3 things: a plus sign, a 4, and a 7. Please ignore for now that single quote, which will hopefully become clear to you a bit later on. But for now, just believe me that that is a list of a plus sign, a 4, and a 7. We're going to put those things into a name called s. When we ask what s is, it's going to print out plus 4, 7, because those are the things we put in. And when we ask Scheme to eval s, well, maybe have a guess. What it's going to do is run that as if it was code. So that plus 4, 7 does indeed look a bit like a piece of code, doesn't it? But when we pass a list into eval, it evaluates it as if it was code. It gives us back the answer as if we'd just written that code itself. But all we did was write a list and ask it to evaluate it. Yeah, so that's part of the how easy it is to sort of flip-flop between something being data, a list, or being code, something that got executed. So let's define ourselves a function called switchOp. What switchOp does is it takes in A, which is going to be a list, and it sticks together two things. It basically takes the coulda of A, so everything in A except the first thing, so like the tail of that list, and it sticks that together with star. Again, ignore that single quote for now, we'll get to that. Essentially for now, just think of that as a star. So it's basically saying stick together a star at the beginning of a list, and then the rest of the list is going to be everything in A except the first thing. So essentially we're removing the first thing and replacing it with a star. So now let's apply switch op to S. So S is that plus 47 that we had before. So let's apply switch op to S. So run that function above, pass in S as the argument, and then store the answer in S2. Now when we ask what S2 is, maybe you can guess what it's going to say. What it's going to say is star 47. So basically replace that plus sign with a star, or a multiplying sign. Now we can ask it to eval S2, and you might be able to guess the answer. The answer is 28, because now we've replaced that plus sign with a times sign. When we ask to evaluate that list, i.e. treat that piece of data, which is a list, as code, now it multiplies, because star means multiply. So data can be easily treated as code. And indeed, code can be treated as data, and we'll get to that really soon, because remember I told you to forget about that single quote. Well, that's to do with this thing called quoting, which is possibly the coolest thing in Scheme that there is. So we'll talk about quoting, we'll talk about how you can name stuff pretty cool in Scheme. We'll talk about duck typing and how that allows you to write generic code very easily and quickly. We'll talk about lambdas and closures, which are like functions that can hold useful stuff inside them, and we'll talk even more about metaprogramming, going further than what I was saying about meta functions, and just how cool it is. So this is the section in which I tell you it's worth dealing with all that weird stuff I just told you about, because here's where I tell you how cool Scheme is, so it was all worth it. So let's start with quoting. Now this is something that you basically don't get in other languages. So there are some languages where you can write a bit of text in quotes, and then later you can call a function called evaluate or eval or something like that, and it runs that as if it's code. What's cool in Scheme is that you're not just giving it something in quotes, you're giving it a piece of parsed actual code, which you know is kind of syntactically okay. And you can manipulate it as a list, and then later on evaluate it as a piece of code, and you know its structure is going to be right for Scheme to evaluate. So the way you quote stuff in Scheme is you put a single quote and then something else. So the something else can itself be a bracketed or even a nested set of bracketed stuff, and what Scheme does is it looks at the next thing after that quote, and it treats that not as a piece of code it's going to execute, but as a list of stuff that you might execute later. So for example, if you say quote this thing, and then the this thing is basically an open bracket, a star, a 3 and a 6, it gives you back a list of star 3, 6. And if we say quote this whole great thing, but it's all one thing, right, because that open bracket doesn't end until right at the end of the line, that quote symbol will apply to the whole of that stuff. It won't run any of the code inside there, because all of it's quoted. So when we ask for quote of foo bar A3, we get back a list of foo and another list of bar and A and 3 in it. And that's the way the evaluator displays that to us, but really those are just a list with another list inside it. And that's it. You can, once you've got this power to create code that you're not going to run yet, you're going to manipulate or do stuff with, and then evaluate it later. The power that's in your hands because of that is massive. You can stop writing boring old code that looks pretty similar to some other piece of code, and instead just generate it on the fly, and not in the way that you've had to generate code in the past because you had some extremely boring code to write in some old-fashioned boring language that was invented 20 or 30 years after Scheme, where you generate a whole load of source code which has probably got bugs in it, and then compile it, and then try and hook up the compiled code with your other code, and it generates wrong, and then you end up checking the generated code into your source control, and then wishing you hadn't, and so on and so on. No, in Scheme it's clean, it's beautiful. You can do jobs like that without leaving the language, and without needing to generate code in some other place. The code that you're generating is in memory in a list, and then you can immediately make it part of your program. Other things that are cool about Scheme, well, how about these names? All those names in that list, including things with exclamation marks in and stars in the middle, or hyphens, or something like less than 10. Those are all valid names for things in Scheme. Scheme knows that everything you write until you type a space is part of the name you're defining. If you're thinking that that's awful and horrible, you're wrong. That's really cool. Notice also that plus is a name, and actually plus is the name of a procedure in Scheme, or a function. It refers to a built-in function in Scheme, but it is you can treat it like another function. In fact, you can do something like this. Let's define a function called plus that takes two arguments, x and y, and define its return value to be 5. Now when you add together 2 and 2 by calling the plus function, you've replaced the built-in plus function that came with Scheme with your own one, which always returns 5. So when you ask what 2 plus 2 is, the answer is 5. Now, you might think that's awful. Actually, it's cool. And it also can be useful, right? Because you might want to be able to add together things that Scheme doesn't know about. You can actually replace the built-in plus function with a plus function that knows about your stuff and also delegates to the normal plus function if it's dealing with normal stuff. So you can do some pretty cool stuff with that. And that stuff is something around duck typing. So duck typing is the idea that you can write code which basically says if it quacks like a duck, then it's a duck, and doesn't worry too much about what type of thing it is. It just says, I'm allowed to do this type of operation with it. So an example is the built-in sort function that we've already seen. That takes in a less than, which knows how to compare the things that you gave it. So when you give it a list of numbers, you give it the less than function as its argument, second argument, and it uses that less than to sort the stuff in the list. But if you've got a list of some other type of thing, for example strings, you can call exactly the same sort function, but pass in the string less than question mark function. Yes, that is all just one name. String less than question mark is just the name of the function. And sort will happily call that string less than function in order to do its comparisons, in order to sort that list. And it won't have to worry about, what's the type of these things? It trusts you. You passed it in a list with some stuff in, and you passed it in a function that ought to be able to take in those things and compare them. And indeed it can in this case. So it quite happily sorts that list of strings. Exactly the same code. That sort function only needs to be written once, but can be used on any type of thing, even things that you made yourself that look nothing like the built-in stuff in Scheme. That's cool. Although these days is not that new, because if you write code in a language like Python, you can do all that stuff anyway. Other stuff. So something that's been added to a lot of languages that were invented 30 or 40 years after Scheme, which Scheme has had since it was invented in the 70s, is this idea of something called a lambda function. Effectively, a lambda function is a function that you haven't bothered giving a name. So really, it's not as clever as it sounds. So the way you make a lambda function in Scheme is you do open bracket and then you type the word lambda, and then you open a bracket and give the list of arguments that lambda operates on. So you're defining a function right here. So this is, you're saying, in this case, the stuff in red means make a function which takes an argument called x and return. What that function does is returns plus x1, as in x plus 1, 1 more than x. The reason why you might want to do this is because you can't be bothered to go off somewhere else and define a function that adds 1 to x, because it's such a simple thing to do. You want to express it right here and now. So in this case, what we're actually doing is we're calling map, and map takes in a function and a list. So the list we're passing in is 1, 2, 3. The function we're passing in is this function that we've defined right here, which adds 1 to x, and the answer you get back is a list with 1 added to everything in the list. So that's cool. It must be cool because it's been added to all of the boring, old-fashioned modern languages that were invented so long after Scheme, because they eventually realised Scheme got it right in the first place. So another thing that you get in some modern languages these days is something called a closure, which is basically a closure is a word from maths, meaning you kind of can't end up somewhere you shouldn't be, is maybe the way to express it in a way that makes sense for what we're talking about here. So you can't, maybe that's unhelpful. Anyway, what a closure effectively comes down to is when you define a function, it has access to the names that it can see at the point of its definition. That's something called lexical scope, which, by the way, was pretty new in the time of Scheme, and is now so non-new to those of us who use normal programming languages that it's hard to imagine a situation where lexical scope didn't apply. Anyway, a closure means when that function was defined and it could see stuff, if you then return that function or use that function in some other way, especially if you return it as the return value of some other function, the stuff it could see, it will still be able to see. It doesn't kind of get lost. So that's why I was referring to the mathematical concept of a closure, is that you can't perform operations that end you up outside of a reasonable place to be. In a similar way, a closure means when you return a function and then try and run it later, it will still work because it still has access to the variables that were visible to it at that point of its definition. So all of that is probably horrifically incomprehensible, but hopefully it will become clearer as we look at this example. So here we're defining a function called counter. Now notice this is the first function we've seen which doesn't take any arguments at all. So we say define and then open bracket, which means I am defining a function. If there wasn't an open bracket there, we'd be defining a name, but we're defining a function. But this is a function that takes no arguments, so there's a close bracket immediately after the name. It's still a function, it just doesn't take any arguments. And then this function consists of 2 lines of code. Most of the functions we've seen so far only consist of 1 line, but this one consists of 2. The first line defines a name or a variable called C and puts the value 0 into it. And the second line is the return value. So all the rest of the function that starts with lambda to the end, that's this one more line of code, logical line I mean, which is a function which is going to get returned. So so counter is a function that takes no arguments and returns a function. And the function that it returns, we're creating right there using lambda. We're saying lambda open bracket close bracket. So that means this function that takes no arguments again. So this is another function that takes no arguments. So counter takes no arguments, but it also returns a function that takes no arguments. And the body of that function again consists of 2 lines. The first line, it starts with set, and then the second line returns C. So the function counter defines a thing called C, and then the function that counter returns does something to C and then returns C. So what it does to C is changes its value. Now this is the first time we've seen a function that changes the value of something. So what set exclamation mark does is changes the value of C. Previously we've only seen names being given to things and then not having them change. But actually in Scheme you can change the values that are stored in variables. So calling them variables is actually a reasonable thing to do, although it's not something that happens very often. In fact, it's something that the creators of Scheme thought you should be cautious about. So every time you do it, the functions that you call will be called something exclamation mark. So in this case, set exclamation mark changes the value that's stored in C, and what it changes it to is 1 more than C. So plus C1 means just 1 more than C plus 1. So what the function that we return from counter does is increases c by 1 and then returns c. So hopefully we've got enough of a handle on counter that we can see some examples of what counter does when you run it. So I've said that. So let's call counter and put the answer into A. So remember, counter, when you call it, returns a function. So A is itself a function. So now if we call A by putting brackets around it, because that's how you call a function, the answer we get back is 1. But now let's call A again. So do you remember what A does, what the function that we return from counter does? What it does is increases c by 1 and then returns c. So it may not surprise you that when we call A again, we get back 2. So this c, the c that was inside counter and that was getting modified inside the function we return from counter, is part of the closure of A. So A was a function that was returned from counter, but it still makes sense to call A even though we're no longer inside counter, because when we returned A, we also returned all the stuff that A could see, bundled up inside it. So we can't see it, but A can still see that stuff. So when we call A again, we get back 3. So this is why we called counter counter, because it returns a thing that counts up every time you call it. But what happens when we call counter again? It returns a function. So inside a counter, we created this thing called c, and then we returned a function which increases c by 1 and then gives you back c. So any guesses as to what b will give you? Well, what b gives you is 1. And if we call A again, because we're carrying A over from the previous slide, when we call A, we get back 4. So that might be surprising to you, or it might not be, but what you can hopefully surmise from that is that the closure of A is not the same as the closure of B. So A has got a copy of C inside it, which is still counting up and it's got up to 4. But B has got another copy of C in it. So every time you call counter, there's a new closure made for B. Or for each function that gets returned has a new closure inside it, a new copy of C. So that's what closures are, and they're essentially a way of having stuff, kind of state stored inside something which can be changed later, which we'll see used in more sophisticated ways later. So other things that are cool about Scheme that should make you want to play with it and try it out. Well, how about the fact that metaprogramming is just programming in Scheme? It's nothing special, doesn't even deserve a special name that's really long like metaprogramming. And pretty much all the programming you do is metaprogramming, in the sense that you're writing functions that modify functions, or rewrite bits of code and return them in a different form or things like that. So I found it very difficult to find an example that expresses what I mean here. This is the example that I came up with, which is quite a simple case. But here we're going to define a function called times n, which takes in an argument n, and it returns a function which takes in an argument x and multiplies n by x. So the way we can use that is we can call a function called times n. We can call the function times n and pass in the value 3 and put that into a name called times 3. So this is an example, in some sense, of metaprogramming, in the sense that we've created a new function which multiplies things by 3. We've given it a name, times 3. So there's no code anywhere that of a function that multiplies things by 3. There's only this thing called times n. But we called times n, gave it the answer 3, and it gave us back a function that multiplies things by 3. So we've kind of made a new function. It does something new, but all within the code of the language. And then let's do it again. So let's define a function called triple, which takes in a list, and then the body of that function calls map, passes in times 3 as the function for map, and list as the list to apply it over. And now we've got a new name called triple, which is a function that takes in a list and multiplies everything in that list by 3. So when we call triple and pass in a list of 3 numbers, we get back all those numbers multiplied by 3. So again, we've given a name to this new thing called triple, which is built by things that we built by calling functions, returning functions from things like that. So that's what I mean when I say metaprogramming is just programming. We've just written normal scheme code here, but we're able to give names to concepts that in some languages we'd have to step out into some other metaprogramming language to be able to define. Or maybe we wouldn't be able to do it at all. Maybe we'd have to write a ×3, a ×4, a ×5 function for everything we wanted to do. But not in Scheme, you just write it once. And that's why it's so hard to understand other people's code written in Scheme, because they've done so many clever things like this. Did I say that out loud? Okay, so other things I haven't had time to mention, but are also cool about Scheme. Macros. In Scheme, you can define your own stuff that works a bit like if. I remember I said that if doesn't actually run the arguments that you give to it. It only executes the bits of code for the part of the if that actually was the right part to execute. So you can write your code which works in a similar way and does stuff like that. So for example, you could write like a three-way if that does something different depending on whether a number is negative or 0 or positive. And that could look just as natural in the language as if. So macros are cool. Also streams, which are an idea that we would now probably talk about as iterators, or the same ideas have now become something that we normally talk about as iterators or iteration. But writing in a streaming style was something that was actually invented around the time of Scheme, and again, like lambdas and things like that, has been kind of rediscovered relatively recently, pioneered by Haskell and then brought to the masses by Python, and now everywhere. Iterators and iterating through things is a brilliant way to work with potentially infinite length lists or just long lists without having to have the whole list in memory necessarily. Very efficient way of working in parallel, for example. Setting up kind of a chain of operations that happen to each item in a list, things like that. So all those ideas were there and being talked about in Scheme right from the beginning, and we're finally re-evaluating them. Also, they did cool stuff, these people who wrote Lisp, like the circular evaluator, which is a tiny, really not a lot of lines of code, Lisp implementation or Scheme implementation in Scheme, which the inventors of Scheme then used to investigate what if we wrote Scheme in slightly different ways. It's just beautiful. If you like stuff that's self-referential, you're going to like it. Things that are cool. When I say Structure and Interpretation of Computer Programs, the book, often referred to as SICP, S-I-C-P, changed my life. I honestly mean, I've never felt the same since I read this book. It is a beautiful, exciting, thrilling read. Fun, really playfully written, joyful, and a fantastic introduction to Scheme, but also introduction to what computer programs really are, and sparked in me a deeper love of programming than I had before. Highly, highly recommended. Available for free online under a Creative Commons license. By the way, the slides of this presentation are also under a Creative Commons license. So the link at the bottom there, the MIT Press link, last time I tried to use it, it didn't work particularly well. Some of the internal links were broken. But there is a copy that someone has made of this book on GitHub, completely legally because it's under a Creative Commons license. And they've made a PDF of it and things like that. So there are nice ways to read it. Also, why not buy it from MIT Press? Just to help them understand that people still appreciate and love this stuff so much later. No time for questions because there's no one in the room with me. But just a quick note that you can find the source code for this presentation on my GitHub. Also some other Scheme and programming related stuff. You're welcome to use this material for stuff you're doing. under a Creative Commons Attribution Share Alike license. Also, please let me know what you're doing. I'd be very interested. I also have a couple of bonus sections, so we're not quite at the end yet. If you're excited by the ideas we've covered so far, I'm going to touch on a couple of really cool things that are more advanced than what we've talked about so far, but we've covered everything you need to be able to understand them in the preceding presentation. You just possibly, if this is the first time you've seen this stuff, you might want to stop, have a quick cup of tea and then carry on. So I'm showing you these because these really get cool, and I want you to know just how cool Scheme is. So let's start off with a statement I made quite early in the video that data and functions were really just the same thing. There aren't actually two things in Scheme, there's only one, which is just functions, because data is the same thing as functions. So here's how I'm going to demonstrate that. I'm going to write a function called mcons, which takes in two arguments, and the return value of that function is a function which takes in an argument called cumd. And if cumd is equal to car, we return A, and if cumd is not equal to car, we return B. So I've made a function called mcons, which takes in A and B, and it returns a function which itself might return A or B. So it's using the closure property of functions. Now let's define two more functions. Let's call them mcar and mkudur. These by the way, stand for like my. So this is my cons, my car, my kudur. And let's define mcar when you give it a pair, or what we're calling a pair. What it does is calls pair as if it's a function and passes in car. And if we and then we define mkudur to be the same thing, but what we call pair, passing in an argument called kudur. So why would we do all this stuff? Well, here's why. If you call mcons on 1 and 2 and get back the answer and put it into foo, and then we call mcar on foo, so this thing we got back from cons, we call car on it, we get back the first thing. If we call mkudur on foo, we get back the second thing. So you may need a bit of time to figure out why. So first of all, take this in. This is what I'm doing. So mcons takes two things in. And what's the definition of cons? Well, previously we might have thought the definition of cons was a function that gives us back a pair, but we haven't really defined what a pair is. So how about we define what a pair is as being something that you can get the two things out of by calling car and kudur. Well, now mcons surely fits the definition of being of making a pair, because we can get things out of it by calling car or kudur, or in this case mkar or mkudur. So what we've done is we've implemented our own version of const car and kudur without using any of the const car and kudur stuff that exists in Scheme. We've just written it using plain old functions. So let's go back to the plain old functions. So mconst takes in those two arguments and it just kind of holds them in its closure. And then based on whether you call the function it returns with an argument car or an argument kudur, it returns either A or B, or returns one of the two things it was given originally. So all we've done is defined mkar and mkudur to call that function that came back from mconst with one of those arguments. In fact, it doesn't need to pass in kudur in the second case. It could pass in anything because we're only checking for whether it's equal to car. So what we've done is made up pairs, kind of out of thin air, like magic. There's a picture of a wizard on the front of the SICP book, and they like to talk about magic quite a lot. Programming is a bit like magic. In this case, we've kind of made pairs, we've made data out of thin air. Once you've got pairs, you can make lists, as we've already seen, so long as you have some kind of definition of null or the empty list. So what happened to data? It turns out you can think of data as actually just being a type of function. yeah, so take that in. We wrote our own cons, car and coulda. I bet you weren't expecting that if it was the first time you've seen it. So that's pretty cool. But that's not the coolest thing. I'm going to show you the coolest thing now. If you thought that was cool, you're going to think this is cooler. So we made data out of functions. How about trying something else? Let's define a variable called n0 as a function which takes in no arguments and returns the empty list. So why would we do that? Well, bear with me. So we define this thing called n0, and what it is a function that returns the empty list and doesn't take any arguments. Now let's define something called minc. That stands for like my increment. So let's define something called minc, which takes in a value x and returns a function that takes no arguments that returns x. So it just returns the thing that was when you called minc, you got back a function. When you call that function, you get back the thing you were passed in to minc. Okay. So again, bear with me. It may not be clear why. Now let's define something called mdec. That takes in something called x, but what it does, instead of returning a function, what it does is calls x, assumes x is a function, and calls it with no arguments and returns the answer. So you can see how minc and mdec are kind of opposite, because minc returns a function, and when you call that function you get back x, and mdec calls x, calls its argument, assuming that it is a function. So we've made some things. We've made n0, we've made minc, we've made dec. Let's make some more things. So let's make something called n1. And n1 is the answer we got when we called minc on n0. So assume for a second that inc really does increment something. If we give it the 0, we're calling the answer 1. And now let's define an n2, which is the result of incrementing n1, and so on and so on and so on. Now we've got all these things called n0, n1, n2. So let's define ourselves a few more functions. For example, let's define a function called m0, question mark. In Scheme there is a function called 0 without the m at the beginning, 0, question mark. In Scheme, functions which return a yes or no answer normally end with a question mark at the end of their name. So let's define a function called m0, takes in an x, and asks the question, is x null, as in is x the empty list. Now that null is not something we define, that's the built-in null question mark that comes with Scheme. So basically says, when we call x, sorry I missed that part out, 0 asks, given an x, when I call x, is the answer null? You'll remember, I hope, let's go back there, that we defined n0 to be a function that when called returns null. So the 0 function basically calls the thing it's given and checks, is the answer null? So that will indeed return true when you give it n0. Now let's define a function called equal question mark, which takes in x and y and checks whether they are equal. And the way it does that is using a cond expression, which we haven't seen before, but it's like a switch. It's kind of like a switch. So each line is a condition, and then what to do if that condition is true. And the else line always runs if none of the others run. So what cond does is checks whether x is 0, and if so, it returns the answer or true or false based on whether y is 0. So basically, if x is 0 and y is 0, then we're going to get back a true from that. Otherwise, if x is 0 but y is not 0, we're going to get back a false. And then the next line does kind of the opposite. So if x wasn't 0, we move on to the next line, and we ask, is y 0? And then we return the answer, which is basically the same again. So if y is 0, then we will only return true if x is also 0, which of course it will never be, because we would have got into the first condition. So actually, this is always going to return false, that second line. So if x is 0 and y is 0, return true. If y is 0, return false. and then everything else, any other conditions if x and y are not 0, or rather 0, our own made up version of 0, then the return value of m equal is going to be calling m equal again, but the arguments we pass in are x passed into the mdec function and y passed into the mdec function. So you may or may not believe yet that mdec actually decrements our numbers, but remember what mdec does. What mdec does is calls x, and that's the answer. So if we think about what inc does is kind of wraps up x in a function that when you call it gives you back x. So if you call minc and then mdec, you'll get back the same thing you put in. So given that these numbers were made by calling minc, if we used mdec on them, then it will indeed give you the one that's one less. So what we're doing in m equal is saying if they're both 0, then it's true. If one of them's 0 and the other one isn't, then it's false, they're not equal. Otherwise, call ourselves again, but reduce both of these numbers by 1. So hopefully you'll see, assuming we're dealing with non-negative numbers here, that the m equal function will eventually get with smaller, the x and y will get smaller and smaller until eventually one of them's 0, and at that point it'll be able to check is the other one 0. If so, they were equal. Otherwise, they're not. So hopefully you now believe that m equal is a correct implementation of checking whether x and y are equal. So let's test it out. So we can try out giving n1 and n0 to the m equal function, and indeed it does return false, whereas if we pass in 1 and 1 it returns true. So let's do some more comprehensive testing. Let's have a look at a function called m+. So what m+ does is takes in two numbers, or two of these number-like things we're making, and it basically says if the answer, if y is 0, then the answer is x. Otherwise, call ourselves again, but add 1 to x and reduce y by 1. So hopefully you'll be able to see from that, eventually y is going to get down to 0, assuming these are non-negative. And given that we haven't made any negative numbers, we don't know how to. That's a fair assumption. Obviously this could be extended, by the way, to do that, but we haven't done that here. So what plus does is either returns x if y is 0, or calls itself again, but increases x, decreases y, calls itself again. Eventually y will be 0. Therefore the answer will be x, and you'll end up with the answer of adding up x and y. So let's test it out. Let's try adding up 0 and 2 on that first line, and then checking whether that's equal to 2. And what m equal returns is hash t. Oh, I forgot to say, by the way, hash t means true. It's the way the scheme evaluator prints out true when it gets back true. So now let's try adding 0 and 2 and then checking whether that's equal to 3, and the answer is false, so no. And then the third one down, we add 0 to 2 and then we add 1 to 2 and we check whether those things are equal, and indeed they're not. And then in the bottom line we add 2 to 3, check whether that's equal to 5, and it is. So we have made numbers, or at least the non-negative integers, purely from functions. We haven't mentioned any numbers in any of this. The only built-in scheme things that we used were cond, which is like a kind of a chain of if statements, and null, which checks whether something's an empty list, things like that. We've made up numbers out of functions, and if you don't think that that is cool, I don't know how to show you that scheme is cool. That's as cool as it gets as far as I'm concerned. I think it's almost infinitely cool. I hope you agree. And that's it. Scheme is a beautiful, simple, weird and cool language. I hope you enjoyed exploring it a bit. Read the book, and find me on Twitter or some other piece of social media. I love to talk about Scheme. I'll see you there.